In this video, we'll be continuing Module 2, Lesson 3 on propositional logic. And we have another definition here. We'll define what is called the Sheffer stroke. The Sheffer stroke is the logical operator defined by the above truth table. So you'll see we have two propositions, P and Q, and we'll denote this with the vertical line. So P, the vertical line, and then Q, that's the Sheffer stroke. And what it does is it gives true for all cases except when P and Q are both true. When P and Q are both true, then it is false. So it's defined by this truth table. And we're going to complete the following tasks. First, prove that the Sheffer stroke is equivalent to the negation of P and Q. So let's start a truth table with two propositions, P and Q. So we'll have 4 rows in our truth table. And we're going to let P be true, true, then false, false, and let Q be true, false, true, false. And above, we are shown that this stroke is going to give us false for true and true everywhere else. So this is its truth table. And we want to prove that it's equivalent to the negation of P and Q. So first we'll find P and Q. P and Q will have true and true is true, true and false is false, false and true is false, false and false is false. And so we can clearly see that this is correct. This is the negation because we'll change true to false, false to true, false to true, false to true, and then it exactly matches the truth table that we had for the Sheffer stroke. We're also asked to prove that not P is logically equivalent to taking the Sheffer stroke of P with itself. So let's put not P in our table. Not P, of course, is going to be false, false, true, true. And the Sheffer stroke of P with P, so I'm imagining that I have this column for P twice. So the first line will be true and true, that's false. The second line will be true and true, that's false. Then we'll have false and false, which is true, false and false, which is true. So we can see that these are equivalent. I can also do the conditional statements P implies the Sheffer stroke, or rather, not P implies the Sheffer stroke of P with itself, and the Sheffer stroke of P with itself implies not P. And what we should see is a tautology. So first I have this column implying that column. I have false implies false is true, false implies false is true, true implies true is true, true implies true is true. Or here, similarly, if I go backwards, if I start here and then do the other, I have false implies false is true, false implies false is true, true implies true is true, true implies true is true, and we see that it is a tautology in both directions. So we get to say, because of this, that not P is equivalent to the Sheffer stroke. Next, we're asked to build the conjunction and disjunction using only this stroke. So I'm going to start one more truth table and repeat these first couple of columns, P and Q. True, true, false, false, true, false, true, false. Let's go ahead and put in not P and not Q, just for future reference. So that's false, false, true, true, and false, true, false, true. And I'm going to put this stroke in as well, just for future reference. So the stroke, the Sheffer stroke, is true and true is false, true and false is true, false and true is true, false and false is true. And I was asked to build conjunction using only this stroke. Well, I know something already about how conjunction is related. I have this equivalence that we found in part A. So it looks like if I had maybe negation of P and the Sheffer stroke with, or rather just the negation of this guy. So let me back up. Since the negation of the conjunction is the Sheffer stroke, the negation of the Sheffer stroke should give me the conjunction. So let's try that. I'm just going to do negation of P Sheffer stroke Q. Well, that should be true, false, false, false. And just to compare, let's see the conjunction P and Q. P and Q, true and true is true, true and false is false, false and true is false, false and false is false. So this will be how we build the conjunction using just this stroke. We just take its negation and that will give us the conjunction. Next, we want to build the disjunction. So I'm going to do not P, its Sheffer stroke with not Q. So false and false is true. False and true is true. True and false is true. And true is false. That is again just applying this stroke to these two columns, not P and not Q. And then we'll remind ourselves what the truth table for the disjunction P or Q looks like. Now I'm looking in the first two columns. So I have true or true is true. True or false is true. False or true is true. False or false is false. And again, we can see that these match. So this is how we'll build the disjunction P or Q using only this stroke. So that is the answer to that exercise. I'm just going to summarize here at the bottom. The negation of this stroke is logically equivalent to the conjunction, and negation P, Sheffer stroke negation Q is logically equivalent to the disjunction or. Okay. So a little bit more about the laws of logic. We're going to list some of the most basic equivalences, and we'll have a table right after this. But we want to point out that we're pretty comfortable at this point with the laws of algebra, like commutativity, associativity, distributivity. And the laws of logic are quite similar. Another thing that we'll note is what's called duality. And what it says here is that, notice that with one exception, the laws are paired in such a way that exchanging the symbols conjunction, disjunction, true, false, for disjunction, conjunction, false, true, respectively, in any law will give you a second law. So for example, we have P or false if and only if P. And that should result in P and true if and only if P. This is called duality. So I replaced my disjunction by conjunction, my false by true, and the law still holds. So these two laws are dual to each other, and that is what is called duality. And we also want to note that we are a little careful when we apply duality to the conditional operator, because we also have to take the converse. So it's not enough to just replace disjunctions by conjunctions. So for example, the dual of P and Q implies P will be P or Q, and when I switch this arrow, I will now say is implied by. So P or Q is implied by P is the same thing as saying P and Q implies P. And you see the second one, P or Q is implied by P, can also be written just as P implies P or Q. So notice how this differs from this. We can, of course, use the truth tables to verify any of these laws. And here's the table that I mentioned. So you'll recall I mentioned commutativity. When I'm doing conjunction or disjunction, it doesn't matter whether I'm doing P or Q or P, they're the same. P and Q versus Q and P, they're the same. Associative laws, it doesn't matter whether I first do P or Q, then or R, or if I first do Q or R, then or P. And the distributive laws we saw in the last video, that the conjunction will distribute over the disjunction and the disjunction will distribute over the conjunction. So if I see P and, then in parentheses Q or R, I could expand that to be P and Q or P and R. Similarly, if I have P or Q and R, that can be P or Q and P or R. So as I mentioned, these are very similar to the rules that we're already familiar with in algebra. And there are several more rules here which I'll leave to you to study this table. And one very important law that you're going to want to know is the De Morgan's law. This will come up all the time. We talked about the negation law, which is basically that P and not P is a contradiction. So these are the ones we've talked about, but all of these are going to come in handy to use whenever you want. So definitely should spend some time getting to know these, and I'm sure as you practice doing your exercises and in the exercises that we'll do together, you'll get some use out of these. Okay, so here we have an exercise that says write the following in symbolic notation and determine whether it is a tautology. If I study, then I will learn. I will not learn, therefore I do not study. So this is one compound proposition. Let's start by assigning names. So I'm going to let P be the proposition I study. Then negation P would be the proposition I do not study. And we'll let Q be the proposition I will learn. And so negation Q, or not Q, will be I will not learn. P implies Q, or if P then Q, will be if I study, then I will learn. So what we have, if we want to translate this into symbols, is going to be P implies Q, because I have if I study, then I will learn. I'm going to put that in parentheses because I also have and I will not learn, so not Q. Therefore, I do not study should be implies not P. And then we're asked to determine whether or not this is a tautology. So let's go ahead and create a truth table with two propositions, P and Q. So we'll have 4 rows. And as always, I'll put true, true, false, false in the P column, then true, false in the Q column. I'm going to put not Q and not P because I know that I'm going to want these. So let's do not P and not Q because these are going to come up later. So not P is false, false, true, true, and not Q is false, true, false, true. Let's also do P implies Q. P implies Q will be true, false, true, true. So then I'll do P implies Q and not Q. So I'm looking at these two columns. This is going to be false, 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 true. Finally, I want to see if P implies Q and not Q implies not P is a tautology. So I'll shift my focus to these two columns. So first I have false implies false, that's true. False implies false is true. True implies, I'm going backwards, I apologize. So from this side to this side I have false implies false, which is true. False implies false, which is true. False implies true, it's also true, and true implies true is true. So this is a tautology, which means I get to upgrade to my double arrow. Now if we look back at the table above, I will actually find this tautology here in my laws of logic, and this is called indirect reasoning. And this is one of the laws of logic. So let's revisit that statement. If I study, then I will learn. I will not learn, therefore I do not study. That's a perfectly true statement. Now, show that the common fallacy P implies Q and not P implies not Q is not a law. So going back to the previous example, we had P implies Q and not Q implies not P. So the next problem is telling us that if we switch these two, if I put not P here and not Q there, then we're no longer a law of logic. Let's see that. So I already have the truth table above for P implies Q. Let's see P implies Q and not P. And I'm going to use the truth table I already created to help me out. So P implies Q and not P is going to be true and false, false and false, then true and true, true and true. So that was true and false, false, false and false, false, true and true, true, true and true. Okay? And then I want to see P implies Q and not P. And let's do implies not Q. So I'll be comparing this column. This is the not Q column. So I have false implies false. That's true. Then I have false implies true. That's true. Then I have true implies false, which is false. And finally I have true implies true, which is true. So you can see this is not a law of logic because of the third case where I get false. The problem tells us this is a common fallacy. So if we looked back at our previous example, this would be, if I study, then I will learn, and I do not study, therefore I do not learn. This is not always true. So there could be the situation where you don't study, but miraculously you learn anyway. Okay. Next, describe in general how duality can be applied to implications if we introduce the symbol, the backwards double arrow, and that's read implied by. So this is what it was talking about further up here, when we had to be careful when we were using duality in terms of the conditional operator, because we also have to swap that arrow, which means introducing this new symbol, and we say implied by. So when applying duality to implications, we have to take the converse. Or change the direction of the arrow. So we introduce this new arrow, which is the backwards arrow, and we read, instead of P implies Q, this would be P is implied by Q. The final exercise will ask us to apply this duality to the following statements. So we have A, P and Q implies P. So we know that we want to replace the conjunction and by the disjunction or. So I'm going to make that P or Q. But now I have to switch this arrow. So I have to say is implied by P. Another way of saying that is P implies P or Q. Now B is a little bit more complicated. we have P or Q and not Q implies P. So in this case, I'm going to think of the P or Q as just a single proposition. We didn't have to change anything with respect to the single propositions. So the conjunction that I'm going to change is going to be this middle one. I'm going to make this now or, and then I keep not Q. But I switch my arrow. So now I have P or Q or not Q is implied by P, which is logically equivalent to P implies P or Q or not Q. But now let's think about the laws that we learned. We learned that associativity law, so this should be equivalent to P implies P or Q and or not Q by associativity. This was duality. This was associativity. And then Q or not Q is just tautology. So this is simply P implies P. If we go back and we look at our laws, we'll see that P or 1 is just 1. So since P or tautology is tautology, this should actually just be P implies tautology. And then we're done. So that is the last exercise here, and we'll move on to the next section in logic for the next video.